So, imagine you're trying to calculate like orbital mechanics, right?
Okay, sure.
But every time the room temperature goes up by just a couple of degrees, your calculator literally forgets the number 4.
Oh, wow. Yeah, that would be a nightmare.
Right. Like you punch in 2 plus 2 and it spits out 3.8, then 3.5. It just, starts guessing.
Yeah.
And that is actually the brutal reality of analog AI chips right now. We demand billions of calculations a second, but we're building these systems out of physical materials that warp and degrade and drift the moment things get even a little warm.
Exactly. It's a massive issue.
So welcome to today's deep dive. For you, the listener, we are exploring a really dense stack of technical documents today on analog in-memory computing, or AIMC. And our mission is to unpack a radical new framework, specifically a desk product and design manifesto called Inverted Man-ML, invented by Ollie in the summer of 2026.
Yeah, and it's a fascinating read.
Yeah.
Because it proposes a complete inversion of how the microchip industry operates right now.
Right, because right now we're basically fighting the physics, aren't we?
Oh, absolutely.
Yeah.
Engineers treat these physical imperfections in the hardware as, like, a mortal enemy. They spend millions of dollars and just massive amounts of energy trying to force analog components to behave with perfect digital precision.
Which is kind of impossible.
Yeah, you can't beat physics. But what Ollie's Inverted Man-ML patent proposes is, well, it's letting the hardware be naturally, chaotically imperfect.
It's accepting the mess.
Exactly. Accepting it and then shifting the burden of perfection entirely over to the algorithmic software layer.
Okay, so before we get into exactly how Ollie's solution works, we really need to understand why this is even a problem in the first place. Like, why are we even bothering with AIMC?
Right.
And it all comes down to something called the von Neumann bottleneck. So walk us through what that actually looks like physically inside a computer.
Sure. So think about a standard computer architecture. You've got the memory.
Like your digital SRAM or DRAM.
Exactly. That's where all your data is stored. And then, completely separate from that, you have the processing unit, the ALU. That's where the actual math happens.
Okay.
So in traditional AI workloads, like if you're running a massive large language model, your processor is mostly just sitting there idling.
Just waiting.
Yeah, waiting for data.
Yeah.
The system has to physically shuttle a weight from the memory across a copper bus into the processor, do one single multiplication, and then shuttle a result all the way back.
It's just an insane logistics problem. I was thinking about it like having a brilliant chef standing in a kitchen, right?
Oh, I like that.
But every single time they need like a grain of salt or a slice of onion, they have to run all the way across town to a warehouse to get it.
Right, yeah.
Bring it back, chop it, and then run the chopped onion back to the warehouse.
Exactly. And that transit, that running across town, requires a massive amount of energy.
Just moving the data.
Just moving it.
Right.
Accessing a standard 1 kilobyte block of digital SRAM costs about 1 picojoule per byte.
Which, a picojoule sounds tiny.
It is tiny. But when an AI model requires trillions of these operations every single second, the energy cost of that transit absolutely dwarfs the energy cost of the math itself. The von Neumann bottleneck isn't just a speed limit, it's a massive energy crisis.
Which is what brings us to analog in-memory computing.
Right.
The promise here is that we basically stop shuttling the data across town. We just do the math inside the warehouse.
Exactly. We compute where the data lives.
But okay, how does that actually work? Because we don't have traditional logic gates in there. Where is the math happening?
Well, it utilizes the fundamental laws of physics natively in the material, specifically Ohm's law and Kirchhoff's current law.
Okay, physics class throwback.
Yeah, but it's brilliant. So in an analog crossbar array, you have a grid of microscopic wires. And at every single intersection of that grid, there's a memristor.
A memristor. So like a resistor that can remember its resistance state?
Precisely.
So instead of storing a digital 1 or 0, like with a flip-flop circuit, we're storing a continuous value.
Right. Based entirely on how easily electricity can flow through that specific intersection. The mathematical weight of the neural network is physically programmed as the conductance of that material.
Okay, that makes sense. So how do we actually do the math with that?
Well, that's where Ohm's law comes in.
Right.
Current equals voltage times conductance.
Right.
So the input data to the neural network is applied as a voltage to the rows of the grid. As that voltage hits the memristors, a specific amount of current flows through. And just by doing that, it naturally performs the multiplication step.
Literally just by the sheer physics of electricity.
Yeah. And then Kirchhoff's current law takes over. It says that the total current entering a junction has to equal the total current leaving it.
Okay.
So all those individual currents flowing down a single column naturally sum up at the bottom.
Oh, wow. So the multiplication happens at the intersection and the addition happens as it flows down the column.
Exactly. It computes a complex matrix vector multiplication instantaneously.
In O of one time? I mean, the math happens literally as fast as electricity flows from point A to point B.
Yeah, and the energy savings are just staggering. A calibrated analog array can hit 1 to 10 TOPS per watt.
That's tera operations per second per watt, right?
Right. And to put that in perspective, standard GPU workloads are sitting way down at 0.1 to 0.5 TOPS per watt.
So it's consuming tens of femtojoules instead of picojoules.
Exactly. And this is a massive, but here is the reality of the physics. You run into massive non-idealities.
Because analog is messy.
Incredibly messy. In the digital world, we have 8 to 16 bits of perfectly clean precision. In the analog world, current technology hits a hard precision wall at about 4 to 6 bits.
Right, because you're dealing with real physical materials now, not just abstract binary logic. A digital switch is just definitively on or definitively off.
Exactly.
But an analog memristor is trying to hold this highly specific intermediate state of resistance.
And that state is extremely fragile. Take temperature, for example. Without some really heavy calibration, a crossbar array can see a 5 to 15% performance degradation for every 10 degrees Celsius increase in temperature.
Wow, every 10 degrees.
Yeah. The heat literally changes the atomic structure of the conduction channels inside the memristor.
So the chip just gets a little warm, the resistance changes, and suddenly your AI is spitting out bad math.
Exactly. And it's not just temperature. There's also the issue of sneak path currents.
Okay, sneak path currents. I read about this in the sources. What exactly is sneaking and where is it going?
Well, electricity is lazy, right?
Yep.
It always seeks the path of least resistance.
Sure.
So in a dense grid, you might apply a voltage to a specific row, intending for it to flow through one specific memristor into a column. But if a neighboring memristor happens to have a really low resistance state,
It takes a detour.
yeah, the current can actually flow backward through that unselected node, travel along another row, and sneak into your target column from completely the wrong direction.
Oh man, so the controller at the bottom of the column is measuring the current, thinking it's the right answer, but it's actually polluted by rogue electricity.
Exactly. It completely degrades the noise margins.
Woo.
And then you add parasitic resistance on top of that.
That's the IR drop, right?
Right. The copper wires themselves have electrical resistance. By the time a voltage pulse travels from the edge of the chip to the dead center of a massive array, it's lost some of its strength. So the memristor in the middle isn't even getting the voltage you think it's getting.
So, given all this, what has the industry's solution been up to this point? Because it seems like they're just using brute force.
Oh, totally. They're treating these chips like wild, unpredictable animals and basically just trying to lock them in iron cages.
Right.
To fight the IR drop and the sneak paths, they designed these incredibly complex routing schemes. And to fight device variability, they use differential 2T2R cells.
2T2R. So that's 2 transistors and 2 resistors for every single neural network weight. Wait, so instead of one intersection doing the job, they use 2 complete sets of components just to average out the error.
Yes, they run the positive signal through one, the negative through the other, measure the difference, and just hope the physical noise cancels itself out.
But doing that immediately doubles your physical area.
It does. It doubles the area, it increases the energy overhead, and it slowly just erodes the very benefits that analog computing was supposed to give us in the first place.
It's like taking a wildly creative, fluid artist, the analog chip, and forcing them to paint by numbers for digital precision. And we're spending all our money just building the paint by numbers grid.
That's a perfect analogy.
Which finally brings us to the core of today's deep dive, the document titled Invercarad MAML.pdf. This is Ollie's July 2026 patent.
Right.
And Ollie is explicitly clear in the documentation. He acknowledges that right now, in the summer of 2026, this is a desk product, a paper product.
Yeah, it's very much a theoretical framework at this stage, accompanied by a really basic macro scale prototype.
Yeah.
But conceptually, the pivot here is huge.
What's the pivot?
Moving from physical mitigation to algorithmic compensation.
Okay.
Instead of building a perfect, rigid hardware grid to keep the math clean, Ollie proposes a hybrid atomic triad that actually learns its own flaws.
And it does this using MML meta-agnostic meta-learning, embedded in a sparse digital control layer.
Exactly.
So I know basic machine learning relies on backpropagation, right? It looks at the final output error, goes backward through the network, and tweaks the weights bit by bit. How is MAMML different from that? Why the word meta?
Well, standard backpropagation is about learning a specific task from a massive data set. MML is about learning how to learn.
Learning how to learn.
Yeah. In traditional AI, MML searches for this highly sensitive initialization point, a specific state of weights where just a tiny microscopic update will rapidly adapt the network to a completely new problem.
So standard AI is like training a specialist to do one single job perfectly over 10,000 hours.
Right.
But MNL is like training a generalist who only needs to look at a new problem once or twice to instantly figure it out.
Precisely. Now, what Ollie's patent does is take that concept and completely invert it.
Inverted OML.
Right. Traditional MML adapts digital software to new data environments. Inverted ML adapts the digital control layer to a decaying physical hardware environment.
Okay, so let's break down how this desk product physically structures this. The manifesto describes a hybrid atomic triad. It basically completely abandons the idea of one giant perfect matrix.
Yes. Instead, you have 3 interconnected matrices,
Yeah.
and they're governed by a digital controller.
So we have the primary analog calculation matrix.
Matrix 33.
Right, matrix 33. And then we have a dual branch correction system, matrix 3 and matrix 8.
That's the triad.
And a really crucial detail that jumped out at me in the sources. The documentation is clear that all 3 of these matrices are roughly the same size. Matrix 33 isn't some massive behemoth, while 3 and 8 are just tiny side accessories. Why is the proportional sizing so important?
Because the nonlinear errors generated by the physical hardware are just as complex as the primary data itself. Yeah. Matrix 33 holds the frozen deterministic weights, let's say the parameters of an LLM. But as Matrix 33 physically drifts due to temperature or voltage droops, it generates errors. If you just applied a simple linear mathematical fix, it wouldn't be nearly enough.
Because the physics of failure aren't linear.
Exactly.
Yeah.
Physical decay creates these really complex issues like XOR dependencies or S-shaped saturation curves.
Can you give me an example of that?
Sure. An XOR dependence in exclusive OR is a classic nonlinear problem. If the temperature goes up, let's call that condition A, or the voltage drops, condition B. The error might behave one specific way. But if both happen simultaneously, the error might completely invert itself.
Oh, I see.
A straight line linear calibration cannot mathematically map a curve like that.
So Matrix 3 and Matrix 8 act as a literal neural network whose only job is to watch the main neural network fail, figure out the complex shape of that failure, and counteract it.
That's exactly it. Matrix 3 acts as the first stage, projecting the input signal into a hidden space to untangle those nonlinear issues. And then Matrix 8 transforms it into a higher order correction vector.
And here's the absolute genius of the architecture for me. The forward pass, even for the compensation matrices, runs at the exact same high speed as the main calculation matrix.
Yes.
The compensation is happening forward at full speed entirely in the analog domain.
Which means it's incredibly efficient.
Right. It's not stopping to ask the digital CPU, hey, am I drifting? For every single math problem. Because if it did that, we'd be right back at the von Neumann bottleneck, wasting energy moving data back and forth.
Exactly. The high-frequency data throughput remains strictly analog. The manifesto actually describes this as having built-in proprioception.
I love that term, proprioception. It's a biological concept for you listening. It's your body's inherent ability to perceive its own position in space. Like, if I close my eyes, I still know exactly where my hand is.
Right, because your nervous system has this continuous low-level feedback loop that doesn't require conscious, high-level brain processing for every micro-movement.
Right. It's like, imagine you're driving a car down the highway at 80 miles an hour.
Okay.
And the car's alignment is slightly off, pulling to the left. You don't consciously pull out a calculator every millisecond to do physics equations on steering torque. Your arms just naturally hold a slight, continuous counterpressure.
Yeah, that's a brilliant visualization.
That counterpressure is the analog correction matrices, Matrix 3 and 8, while your conscious mind focuses on the road at high speed.
Yes. The atomic triad itself is handling the moment-to-moment drift correction analogously. And the conscious mind in your analogy, that's the sparse digital controller.
Okay, so what is the sparse digital controller doing?
It operates with a memory bandwidth that is orders of magnitude lower than the analog matrices. It only steps in for slow, intermittent fine-tuning, like taking the car to a mechanic once a month.
Okay, mathematically that sounds brilliant, but software simulations always assume a spherical cow in a vacuum, right?
Of course.
If this triad is so great, why hasn't Ollie just built a microscopic 28-nanometer silicon chip to prove it?
Because fabricating a custom 28-nanometer wafer costs millions of dollars, and it takes months of lead time. You just don't take a conceptual theoretical framework straight to silicon.
You have to prove the control principle first.
Exactly. And that is why Ollie's Summer 2026 desk product takes the form of a macro-scale printed circuit board, a 3x6x6 PCB.
Literally a physical sandbox built with off-the-shelf components.
Yeah, it's pretty clunky compared to a microchip.
The documentation gets incredibly specific here. Matrix 3 is constructed as an 8x6 array. That's 6 data rows, 1 reference row, and 1 bias row. Matrix 8 is a 7x6 array, 6 data rows, 1 bias row.
And it utilizes very specific discrete components, MCP6024 quad op amps and DOX3134A multipliers.
Okay, let's unpack that. Why the MCP6024 specifically?
Right.
Why does the choice of op amp even matter that much in a macro prototype?
Because the entire premise of inverted MAML is measuring and correcting microscopic physical drift.
Right.
The MCP6024 is a high-precision, low-noise operational amplifier. If you used a cheap, noisy op-amp, the digital controller wouldn't be able to tell the difference between the actual memristor drift it's trying to correct and just random electrical noise being generated by the op-amp itself.
Ah, I see. The measurement tool has to be cleaner than the error it's measuring.
Precisely.
That makes perfect sense. And the sources say they're operating on a 1.65 volt virtual ground with a 1.90 volt input for the reference rows.
Correct.
But the manifesto is brutally honest about something, which I found refreshing. This PCB is practically meaningless for actual commercial high-performance AI inference.
Oh, completely. It is technically useless for real-world inference right now.
It's just a massive energy hog.
Yeah, it's a slow, energy-hungry proof of concept.
Because it uses gigantic 100 nanofarad discrete capacitors, along with discrete 1 mega ohm and 330 kilo ohm resistors. I mean, in the world of microelectronics, a 100 nanofarad capacitor isn't just a bucket, it's a whole water tower.
Yeah, it is massive. It takes a huge amount of electrical current to charge and discharge it.
So why build it that way?
Because those giant capacitors slow the physics down. The PCB operates on a 10 millisecond refresh window.
Wait, 10 milliseconds. In the computing world, 10 milliseconds is a glacial epoch. Modern processors operate in nanoseconds. Why slow it down that much?
Because they need to observe the control principle in slow motion.
Slow motion.
Yeah, they need an RC time constant, the time it takes for the resistor capacitor circuit to charge or discharge. That is slow enough for a standard digital controller to easily track.
Okay, that makes sense.
For example, the documentation calculates a 0.5 millivolt IR drop on the copper traces of the PCB when running at a 5 milliamp maximum load.
A 0.5 millivolt drop on the physical copper trace.
Yes. And that 0.5 millivolts corresponds to nearly 10% of a least significant bit in the system's precision logic.
So it creates a spatial asymmetry. The math at one end of the board is suddenly 10% different than the math at the other end.
Exactly. And the entire point of this slow motion 10 millisecond PCB is to see if the sparse digital controller can register that deterministic physical deviation.
And then use MML to shift the digital input and output weights.
Right, maintaining mathematical perfection at the system level.
It's testing if the mechanic can actually align the steering wheel while the car is moving.
Exactly.
But there is another major limitation to this 3x6x6 PCB, right? Beyond the energy waste and the slow speed, the matrix is simply too small.
Yes, this is a critical bottleneck for the prototype. The true advantage of inverted MAML, that massive exponential leap in energy efficiency we talked about earlier, that only triggers at a certain scale.
And the sources indicate that scale is likely around a 32 by 32 matrix, or even larger. So right now, with only a 6-column matrix, the computational overhead of the sparse digital controller completely dwarfs the tiny amount of analog math happening in the crossbar.
Yeah, it's like putting a massive supercomputer in charge of a single light switch. The controller uses way more power than it saves.
But I guess if the slow motion mechanics work on the 6-column PCB, the mathematical principles should scale, right?
That's the theory. But the fundamental question is how the digital controller gets its data.
What do you mean?
Well, if it's only doing slow, sparse updates, how does it actually know what the analog hardware is doing during those fast 10 millisecond PCB cycles?
Oh, right. How does it measure the drift without constantly interrupting the AI inference? If it has to stop the math to measure the resistors, you lose the speed.
Exactly. And this is where the architecture introduces what they call hardware anchors.
Hardware anchors.
Yes, these are specific physical cells embedded directly into the arrays, the reference cells and the hardware bias cells.
Okay, let's start with the reference cells. The manifesto states these do not hold neural network data at all. They are hardwired to a fixed 1.9 aerovolt reference potential and connected to a 330 kilo ohm leakage path.
Right. They are deliberately engineered to degrade at a highly accelerated rate.
Hold on. If the whole problem with analog is that the hardware degrades and ruins our math, why on earth are we intentionally building cells that are designed to violently degrade? Doesn't that just pour gasoline on the fire?
I know, it sounds super counterintuitive, but think of it this way.
Yeah.
The reference cells aren't doing the math.
Okay.
They are decoupled from the fluctuating input data of the actual AI model. Over the 10 millisecond cycle, because of that 330 kilo ohm leakage path, they experience a massive, mathematically calculated 78.4% wide sweep in voltage.
Why exactly 78.4%? Is that just like an arbitrary number?
Not at all. It's based on the strict physics of the RC discharge curve. Voltage over time equals initial voltage times to the power of negative T over RC.
Okay, bringing out the equations.
Well, with those specific capacitor and resistor values, over a 10 millisecond window, the voltage drops by exactly 78.4%. And that provides the maximum possible dynamic measurement range without the voltage hitting zero and flatlining.
So they basically act as a dynamic measuring stick.
Exactly. They provide a normalized temporal clock directly from the physical substrate itself.
Oh, that's wild.
Yeah.
So the digital controller glances at how far the reference cell has decayed, say it's currently dropped by 40%, and it instantly knows exactly where it is in the 10 millisecond timeline, independent of any digital clock.
Precisely. And then you have the second anchor, the hardware bias cells.
Right, because in conventional digital neural networks, you always have a mathematical bias term to shift the activation function.
Right, y equals the sum of weights times inputs plus the bias.
Yeah, it shifts the curve so the network can learn patterns that don't pass perfectly through zero.
Exactly. And to do that natively in analog, without requiring a really costly digital summation step at the end, this architecture embeds bias cells physically into the rows of the crossbar.
Okay, but here's the brilliant part. These bias cells use a 1 mega-ohm discharge resistor, which is the exact same discharge resistor used by the standard payload data cells.
Yes. So they experience a highly controlled charge decay. The documentation states it's a droop of exactly 9.52% over the 10 milliseconds.
So they decay synchronously with the actual neural network weights?
Synchronously, yes.
Okay, I see where this is going. Because they decay perfectly synchronously, any ambient physical chaos, say the room gets hot or there's a common mode drift affecting the entire chip, is naturally mirrored in the bias terms.
Exactly. If the temperature spikes and the entire array starts leaking charge, say 2% faster, the bias cell also leaks 2% faster.
It's inherently linked.
Right. So the sparse digital controller looks at that synchronous decay, factors it into the MAML algorithm, and seamlessly stabilizes the network's mathematical output without having to measure every single individual payload cell.
This synergy is incredible, and it ties right back to what MAML actually is, because it's a few-shot learning algorithm, right? It doesn't need a constant high-bandwidth stream of data to understand the environment. It only requires a very few measurement snapshots of those anchors.
It's the difference between needing a continuous 60 frames per second video feed versus just needing 2 photographs.
Let's use a train analogy. If I want to know exactly what a moving train is doing, I could set up a continuous radar lock on it.
But that takes massive bandwidth and energy.
Right. But with inverted MAML, it's like taking 2 still photographs of the train 3 seconds apart.
Yeah.
From just those 2 few-shot snapshots, if I have a smart enough algorithm, I can mathematically calculate the train's exact velocity, its acceleration, and where it will be in exactly 10 minutes.
Precisely. The sparse digital controller grabs a snapshot of the reference and bias cells, does the complex MAML math to calculate the trajectory of the physical drift, and then pushes a low-frequency update to the correction matrices matrix 3 and 8.
Meanwhile, Matrix 33 just keeps humming along, doing the high-speed AI inference completely uninterrupted.
It is a masterclass in separating the logical computation from the physical compensation.
It really is. But, as Ollie's manifesto openly admits, this is a desk product in 2026. There are massive, glaring, unanswered questions before this becomes a commercial reality.
Definitely.
So what happens when you take the training wheels off the PCB?
Well, the biggest challenge outlined in the research revolves around the sparse digital controller juggling 2 conflicting tasks.
Okay, what are they?
First, it has to calculate the drift accurately. But second, it has to cover a sufficiently large matrix, like that 32 by 32 target we mentioned, to actually achieve the exponential energy efficiency that justifies the architecture in the first place.
The duty cycle bottleneck.
Exactly.
The system operates on an optimized time distribution, right? Where the vast majority of the timeline must be dedicated to uninterrupted AI inference. And only a tiny fraction of the time, a highly restricted measurement window between those refresh pulses is allowed for calibration.
Right. It's like a head chef trying to taste test a really complex soup while simultaneously chopping vegetables at light speed.
Okay.
The tasting is the MML measurement window. The chopping is the analog inference.
So if the pot of soup gets too big, say, scaling up to a 64 by 64 or 128 by 128 matrix, the chef spends too much time walking around the pot, tasting different sections and calculating the seasoning.
And the actual chopping grinds to a halt.
Oh.
Exactly. If the matrix scales too large, the digital controller might require too many clock cycles to perform the complex MML calculations. It would basically overrun its designated duty cycle and start stealing time from the inference phase.
Which would bottleneck the ultra-fast analog inference, negating the entire extended advantage of AIMC.
Yes.
So where is the breaking point? Is it 32 by 32, 64 by 64?
We don't know yet. The manifesto acknowledges this is the ultimate unknown in the summer of 2026.
It just hasn't been tested at that scale.
No, it can only be answered by testing real physics, building it out, and pushing the matrix size up until the sparse digital controller finally chokes.
It has to be measured in a real ASIC in step 2. Assuming the 3x6x6 PCB actually flies and proves the slow motion control theory.
Right.
Which brings us to a fascinating thought experiment. Let's assume the PCD works perfectly. The control principles hold, the duty cycle questions are resolved, and the digital controller comfortably handles a 32 by 32 matrix.
Okay, let's assume that.
What does step 2 actually look like?
Step 2 is the leap from a macro-scale printed circuit board to a microscopic application-specific integrated circuit, or ASIC.
A real chip.
A real chip. The documentation lays out a specific roadmap for migrating this architecture to a 40 nanometer or 28 nanometer planar CMOS technology.
The physical scaling here is staggering, because those massive 100 nanofarad discrete capacitors on the PCB, the water towers we talked about, they shrink down to integrated metal oxide metal structures, MOMs.
Like,
we are talking about capacitances of approximately 10 to 30 femtofarad.
which is incredibly small.
Yeah.
A femtofarad is 1/4,000,000th of a farad.
And the physical discharge resistors, the 1 megaohm discrete components, are completely eliminated. They're replaced by controlled sub-threshold channel leakage inside the access transistors.
Which is a beautiful piece of engineering, honestly.
So.
Well, normally a transistor is just a switch. It's on or off. But if you apply a voltage just slightly below its threshold activation point, it doesn't shut off perfectly.
Oh, it leaks?
Yes. A tiny, highly predictable trickle of current leaks through the channel, measured in picoamperes or femtoamperes.
So you are literally using the natural, unavoidable leakage of the transistor as your precision resistor.
Yes,
Yeah.
it's so elegant. But because the capacitance of those MOM structures is so incredibly small compared to the PCB, the refresh window has to shift dramatically.
Right.
The RC time constant plummets. It drops from the slow motion 10 milliseconds of the PCB down to a blindingly fast 10 microseconds to 100 microseconds.
Wait, if the time window drops from 10 milliseconds to 10 microseconds, does the MML algorithm have to be completely rewritten? Like, does the math break down at that speed?
No, and that is the beauty of the inverted MML framework. It scales purely on the relative ratio of the time constants.
Oh, wow.
Yeah, the 78.4% sweep of the reference cell and the 9.52% droop of the bias cell remain mathematically identical, whether it takes 10 milliseconds on a massive PCB or 10 microseconds on a microscopic piece of silicon.
Because the relative geometry of the decay curve is identical.
Exactly. The digital math doesn't care about the physical size of the bucket, only the percentage of water left inside it.
That scalability raises a massive question about integration, actually. If we look at the other research provided in our sources, there is incredible bleeding-edge work being done in material science for AIMC.
Oh, absolutely.
For example, the ACS Nano paper discusses the use of two-dimensional molybdenum disulfide, or MOS2, for memristors.
The 2D layered materials, yeah, they are seen as the holy grail for next-generation analog computing.
The sources state they offer unbelievable energy efficiency, achieving 53 attijoules per operation.
53 attijoules.
That makes the femtojoules we talked about earlier look greedy.
It really does. But the paper also highlights their fatal flaw. They suffer from critical challenges regarding device-to-device and cycle-to-cycle variability.
Because you're dealing with a material that is literally only a few atoms thick, right?
Right, so the slightest manufacturing imperfection causes huge spatial mismatches. They rely on incredibly careful defect engineering.
Which sounds expensive.
Oh, very. The material scientists are literally trying to manipulate individual sulfur vacancies within the atomic lattice just to make the memristor function properly.
They are the ultimate messy analog artist, and currently the industry is trying to solve these variability issues purely through material science. They're spending millions trying to figure out how to deposit the MOS2 more uniformly or engineer the atomic defects perfectly.
But what if we combine the fields? What if we stack Ollie's inverted MML patent architecture on top of that existing ASIC tech?
This is where it all clicks together for me, because it means you take the burden of physical perfection completely off the shoulders of the materials science engineers.
Exactly. They don't have to build a perfect MOS2 memristor anymore.
You build the atomic triad using those highly efficient but highly variable MOS2 memrisors. Then, the inverted ML digital controller dynamically calibrates out the spatial mismatches and the thermal drift that currently plague those 2D materials.
The software layer accommodates the hardware's flaws. Matrix 3 and Matrix 8 would intrinsically learn the specific, nonlinear quirks and atomic defects of that specific chip's MOS2 layer.
That's amazing. They would adjust the forward pass math to compensate for those exact defects in real time at full analog speed.
You basically get to have your cake and eat it too. You get the 53 attajoule energy efficiency of the 2D materials, but because of the MML control layer, you don't sacrifice the strict mathematical determinism required for accurate AI inference.
It creates a true symbiotic relationship. The hardware provides the ultra-low power O of 1-time calculation speed through raw physics, and the algorithmic architecture provides the digital determinism to keep the math clean. It completely bridges the gap.
It fundamentally changes the design philosophy. The hardware engineers can focus purely on speed and energy efficiency, pushing materials to their absolute physical limits, knowing that the inverted MML software layer will catch the errors and smooth them out.
It is such an elegant vision for the future of hardware. So let's just step back and look at the whole picture we've painted today. We started with the von Neumann bottleneck. The stark realization that moving data back and forth from memory to processor is bankrupting our energy budgets.
Which led us to the brilliant but inherently chaotic promise of analog in-memory computing.
Doing the math inside the memory using Ohm's and Kirchhoff's laws saves massive energy, but it traps us in a precision wall of voltage droops and thermal drift.
And the industry trapped itself further by using brute force complex routing and massive 2T2R cells just to fight the physics.
Until we unpacked Ollie's summer 2026 desk product, the Inverted MML Manifesto.
A hybrid system, the atomic triad. Matrix 33 doing the heavy lifting, with Matrix 3 and 8 using built-in proprioception to feel and correct their own flaws at high speed, entirely in the analog domain.
Governed by a sparse digital controller that uses brilliant hardware anchors, the 78.4% sweeping reference cells, and the synchronous 9.52% drooping bias cells.
Right, taking a few snapshot of those anchors to calculate the drift, circumventing the need to constantly monitor every single memristor.
And while there are massive unanswered questions in 2026 about duty cycle bottlenecks and where the system breaks at the 32 by 32 matrix scale, the roadmap is incredibly clear.
Stacking this algorithmic compensation on top of emerging 2D materials like MOS2 could unlock just unprecedented AI processing efficiency.
It completely flips the script on how we design computer chips. We don't need perfect hardware as long as we have perceptive software.
Which leaves us with one final thought to mull over as we wrap up this deep dive.
Let's hear it.
For decades, since the very dawn of the digital age, we have assumed that the absolute pinnacle of computing is perfect, flawless digital state maintenance. We have worshipped at the altar of the pristine binary 1 and 0.
Right, we want our machines to be exact.
But as we look at the human brain, which is still, by orders of magnitude, the most energy-efficient, powerful computer in existence, we know it doesn't work like that.
It's messy.
Exactly. The brain operates on noisy, degrading, chemically imprecise analog signals that constantly self-calibrate and adapt. If inverted MML succeeds in bridging the gap between digital determinism and analog chaos, it raises a profound question for the future.
What's that?
What if the next leap in artificial intelligence isn't about building ever more perfect, rigid hardware, but about designing algorithms that finally allow our silicon to be perfectly, beautifully imperfect?
Wow, imagine that. Letting our chips finally act a little more organic. Well, thank you for diving into the mechanics and the math with us today. Keep questioning the perfect grids, and we'll see you next time.